In this video, we will study the distribution of 10 distinct balls into 3 distinct boxes, and we will find the probability that a box has 0, 1, 2, 3 up to 10 balls. So let us define the random process. We have 10 balls ordered from 1 to 10 on a table, and we have 3 boxes placed in the main box. So we have box A, B and C placed in the main box, and a box is picked at random and a ball is placed in it. The process is repeated 10 times until the table is empty. After that, all the balls are returned to the table and another round of picking starts again. So let us see how this process is working. So first we pick ball 1, and after that we pick a box randomly, and let's say it's box A, and after that we place this ball into box A and we return box A into the main box. After that we pick ball number 2 and we pick a box randomly, and let's say it's box C, and after that we place ball 2 in box C and we return box C into the main box. We repeat this process 10 times until we place all these balls into the 3 boxes randomly. So we repeat that until we place all these balls into the boxes. Now we finished, and this is the end of first round. Now we can start the second round by placing these balls from 1 to 10 here and repeating the same process 10 times. Now let us isolate these boxes with the balls in them and bring them a little bit back, and let us start the mapping process. So we have now ball 1 in box A, so the first letter is A, and we have ball 2 in box C, so the second letter is C, and we have ball 3 in box A, so the third letter is A, and we have ball 4 in box B, so the fourth letter is B, and we keep mapping until we finish all the balls in these boxes. We notice that this mapping is unique in a sense that these letters and the location of these letters reflect the location of these balls in each box. So now let us find all the possible outcomes of distributing 10 distinct balls into 3 distinct boxes. So the sequence we generated is defined over a set, and this set is composed of 3 letters A, B and C, and this sequence is ordered sequence. So if we change the order of letters in the sequence, we will be changing the location of these balls in the boxes. So it means order is important. And the last thing is the objects do repeat in the generated sequence, such as this sequence or this sequence. We can find that B is repeated 4 times, C is repeated 2 times, and A is repeated 4 times. So these 3 conditions indicate that we should use the formula of permutation with replacement. So order means permutation, and repetition of these letters over a set means permutation with replacement. So we use the permutation with replacement R with replacement formula. So this R indicate replacement, and we read this formula as follows: permutation with replacement of n different ordered objects taken R at a time. So let's substitute n. N is the number of objects in the set, so we have 3 objects or 3 elements, and r is the sampling size, and we have 10 objects in the generated sequence. So we substitute in the formula permutation of 3 objects a, b, and c, taken 10 at a time with replacement, and that is equal to 3 to the power of 10. And if we compute that, we get 59,049 possible outcome of that distribution. And this is the number of elements in the sample space for this experiment. So let us use the multinomial expansion theorem to find the favorable outcome of the following events. The first event, 10 balls in box B. The second one, 9 balls in box B. The third, 8 balls in box B, and so on until we arrive at 2 balls in box B, 1 ball in box B, and 0 ball in box B. But we have to remember that 10 balls in box B means that there is a total of 0 ball in box A and C. And 9 balls in box B means that there is a total of 1 ball in boxes A and C, and 8 balls in box B means that there is a total of 2 balls in boxes A and C, and so on until we finish these events. So let us now use the multinomial expansion theorem to find all possible events. We have A and B and C, and A means a ball in A, and B means a ball in B, and C means a ball in C, and this we have 10 balls, so this trinomial here is raised to the power of 10, and that will give us all kind of possible event for this experiment. So if we will place B first and A second, so as we see here, and we will combine A and C together, and we will call them X. Now we will replace A plus C with X. So now we have a binomial expansion of B plus X to the power of 10. So B means there is a ball in box B, and X means there are balls in boxes A and C. So let's now create this expansion. So we have all these events, and let's take this event for example. So this event means that there is 9 distinct balls in box B and 1 ball in boxes A and C. So it could be, this ball could be in box A or it could be in box C. Let us take another event, and that is this event here. So this event means we have 7 balls in box B and a total of 3 balls in boxes A and C. And also for this event, this X to the power of 8 means there are a total of 8 balls in boxes A and C. While for X to the power of 10, it means that there is a total of 10 balls in boxes A and C. So now let us write all these events in order, all these possible events, and let us replace X with A plus C. So we are replacing X with A plus C, and we keep doing that until the last event. Let's take this event for example. So for this event we have B to the power of 3 means we have 3 balls in box B, and A plus C to the power of 7 means we have a total of 7 distinct balls in boxes A and C. Now if we expand this event, we are going to get all these events. So let's take, so this event means a total of 7 balls in boxes A and C, and if we take this event for example, so this event means that we have 4 balls in box A and 3 balls in box C. So now if we want to know the number of favorable outcome of this event, we have to substitute A, B and C with 1, and we get 15,360 favorable outcome for the event of 3 balls in box B and the rest of the balls in boxes A and C. And now let us find the number of favorable outcomes for each event, and that is by substituting B with 1, A with 1 and C with 1. So we do that and we get for the first event 1, and for the second event we get 20. For this event here, 8 balls in B, we get 180. For 7 balls in B we get 960, and we keep doing that until the last event. So for the last events, this is x to the power of 10 or a plus c to the power of 10. This event means that we have a total of 10 balls in boxes A and C and 0 ball in box B, and we have 1024 possibility for it. So let us now add all these favorable outcomes together, and we will get 59,049 possible outcome, and this is the number of elements in the sample space. And this number is not more than 3 to the power of 10. So 3 we have 3 boxes, and 10 we have 10 balls here. So we notice that the sum of all possible outcome is the number of elements in the sample space, and that indicates that all these events create a partition in the sample space. So each event is disjoint from the other event, and their union creates the sample space. So let us find the probability that box B has 3 balls. So we get back to all these events, and we find that here we have B to the power of 3, which means box B has 3 distinct balls. So this is the event we are looking for, and this is the corresponding favorable outcome of this event, and now we divide this favorable outcome over the number of elements in the sample space, and we get 0.26. So now let us find the probability that box B has 5 balls at least. So let's go back to all the events we have. This is the event B to the power of 5. This is the event of box B having 5 balls only. So we want box B to have at least 5 balls. So we may have 5, 6, 7, 8, 9 or 10. And these are the event which constitute the event we are looking for. So these are disjoint event, and their union creates the event we are looking for, which is box B having 5 balls at least. And these are the corresponding favorable outcome. Now we can find the probability of each disjoint event by dividing each favorable outcome over the number of elements in the sample space, as we see. And if we add them together, we get 12,585 favorable outcome of this event here, and that is, if we divide that over the number of elements in the sample space, we get the probability, and that is 0.213. Thank you for watching and have a good day.